Transmitting data across the internet means firing raw electrical pulses into a hostile void, where information is regularly shredded, scattered, or lost forever. The physical layers of the web, the miles of copper wire, transoceanic fiber optics, and invisible radio frequencies make absolutely no guarantees about successful delivery. They exist only to move energy from one point to another. As those signals travel, environmental radiation, thermal noise, and standard signal degradation naturally flip bits, silently corrupting the data passing through the medium. Furthermore, data is chopped into individual packets that take highly varied physical routes to reach the same destination. Because of unpredictable router congestion and raw geographic distance, a packet sent first will frequently arrive last. When a router reaches its absolute hardware limit and its memory fills up, it simply deletes incoming data to protect itself. It issues no warning to the original sender. The packet just vanishes. This creates a severe engineering contradiction. User applications like web browsers, banking portals, and file transfers demand absolute perfection, yet they are forced to run on top of an infrastructure that is physically incapable of providing it. That critical gap is bridged by a piece of software architecture called the Transmission Control Protocol, or TCP. TCP does not upgrade the physical cables or magically fix the hardware. Instead, it acts as a robust stateful wrapper around the application data itself. It achieves the illusion of perfect network reliability through a strict gauntlet of 9 interlocking mathematical and structural mechanisms. By accepting that the physical network is a hostile environment, TCP actively engineers predictability and absolute certainty out of chaotic physics. Before a single byte of application data enters the network, TCP refuses to transmit blindly. It forces both the sender and the receiving machine to explicitly agree on the rules of engagement. This diagram illustrates the first two mechanisms, connection establishment and termination. TCP requires a 3-way handshake to open a reliable channel and a rigorous 4-way handshake to dissolve it, creating a defined state for the communication. This initial synchronization verifies that both target machines are powered on, actively listening, and possess the necessary memory to handle the upcoming data exchange. With the connection established, the protocol immediately confronts its first failure state, data payloads that are mutated or corrupted during transit. Here we see the third mechanism in action, checksums. Before sending, the transmitter calculates a unique mathematical value derived from the data's exact binary contents, appending that number to the packet. Upon arrival, the receiver performs the exact same calculation. If the receiver's result deviates from the attached checksum by a single bit, it proves the payload was corrupted and the packet is silently discarded. The second major failure state involves timing and routing errors, where packets arrive out of order or arrive twice due to network echoes. This buffer interface shows the fourth mechanism, sequence numbers. TCP mathematically stamps every outgoing segment with a unique escalating identification integer. When packets labeled 4, 1, 3, and 2 arrive in the wrong order, the receiver simply reads these sequence numbers to correctly reassemble the fragmented data before handing it up to the application layer. These same sequence numbers enable the fifth mechanism, duplicate detection. If a network echo delivers a second packet stamped with an ID that already exists in the buffer, the receiver instantly recognizes it as a useless clone and destroys it. By enforcing mathematical validation and strict sequential ordering, these mechanisms guarantee that any data passed to the user application is authentic, exact, and structurally perfect. But this creates a new engineering challenge. If corrupted data is deliberately destroyed by the receiver and dropped packets vanish without a trace, how does the sender ever know a transmission failed? This introduces the sixth mechanism, acknowledgment and retransmission. TCP operates on a strict rule that the sender expects a direct receipt for every piece of data it transmits. Every successful delivery prompts the receiver to fire back an acknowledgment, or ACK, creating a continuous feedback loop that ensures no data falls through the cracks. If a packet dissolves in transit, the receiver never sees it, and no ACK is sent. The sender is left waiting, guided only by an internal countdown timer. If that timer reaches 0 before the receipt arrives, the sender assumes total loss and automatically refires the missing packet. However, a hard-coded countdown timer would quickly fail. Internet speeds fluctuate drastically millisecond to millisecond. meaning a static waiting period would be either too impatient or too slow. This dynamic graph visualizes the seventh mechanism, the timeout and retransmission policy. TCP dynamically adjusts its countdown based on the round-trip time, or RTT. The protocol continuously tracks how long ACKs take to return, calculating a precise moving average to calibrate its internal clock on the fly. On a slow, congested connection, TCP widens the window, deliberately waiting longer to avoid spamming the network with unnecessary replacement packets. Conversely, on a highly efficient, low-latency connection, it tightens the timer drastically, allowing it to detect and recover from dropped packets almost instantly. By combining mandatory delivery receipts with constantly updating mathematical time limits, TCP guarantees complete data delivery without overwhelming its own connection. Even with those tools, major network disruptions present a unique threat. If a massive chunk of consecutive data is lost, but the packets sent immediately afterward arrive perfectly fine, the system has a blind spot. Older protocols would force the sender to completely rewind, blindly retransmitting both the missing data and the successful packets, wasting enormous bandwidth. This block diagram demonstrates Mechanism 8, Selective Acknowledgement, known as ACK. When processing a fractured data stream, the receiver issues a specialized signal to the sender. ACK allows the receiver to explicitly state the exact mathematical boundaries of the missing, non-contiguous blocks. Armed with precise coordinates, the sender surgically refires only the missing data, seamlessly patching the gap in the sequence without duplicating effort. Beyond repairing data integrity, TCP must also navigate severe hardware imbalances. If an enterprise supercomputer begins blasting data to a small IoT device, the sheer volume will crush the smaller machine. This capacity meter illustrates Mechanism 9, flow control, and the sliding window. The window represents the exact amount of hardware memory the receiver has available to process incoming data. The receiver continuously advertises the specific window size back to the sender, actively dictating its absolute physical limit in real time. If the receiver's buffer fills up and the window hits 0, the sender is forced to completely halt transmission, protecting the smaller device from a catastrophic data spill. But what if both the sender and receiver possess massive processing power, yet the intermediate routers linking them together are choking on excess global traffic? This final graph maps the last safeguard, congestion control. TCP doesn't just read packet loss and delayed ACKs as mathematical errors. It recognizes them as symptoms of a dying network route. To prevent total infrastructure collapse, TCP proactively slashes its own transmission rate. It throttles its output to alleviate pressure on the shared physical hardware between the two endpoints. Through flow control and congestion control, TCP actively monitors its environment, pacing every transmission against the rigid physical limits of the hardware it relies on. Returning to the macro perspective, the lowest layers of the internet remain a chaotic, hostile environment, defined by thermal noise, broken hardware, and lost signals. But TCP overwrites that chaos. Through strict handshakes, it defines the parameters of communication. Using sequence numbers and checksums, it locks data into verified mathematical alignment. Relying on precise ACKs, dynamically adjusting timeout windows, and selective data replacement, it surgically guarantees that every byte sent is eventually received. And through relentless flow and congestion controls, it continuously negotiates its speed against the unbending laws of network physics. When these 9 distinct systems fire simultaneously, the unreliability of the underlying physical layer is entirely masked from the end user. This engineered certainty, generated through rigorous mathematical statefulness, is exactly why TCP remains the mandatory foundational protocol driving modern cloud computing and global architecture.